My name is Jason Patrick. I'm an assistant professor in the Department of Civil Construction and Environmental Engineering, and I lead the multifunctional composites group, where we're developing material systems that can do more than just structural function, things like self-healing, active cooling, electromagnetic modulation, you name it. We try to put it in a structural package and deploy it to help resiliency of existing structures and new functionalities out in the world.
I'm Alexander Snyder. I'm a third-year PhD student in the Department of Mechanical and Aerospace Engineering. So we've basically invented a way for very typically strong composite structures, say like carbon fiber you'd see in aircraft or glass fiber composites that you see in wind turbine blades, to be even more resistant to common damage they might otherwise suffer, and be able to heal themselves should they become damaged, meaning that we can basically make these parts survive a lot longer in service and make them so that they don't have to be inspected or repaired nearly as often, which is especially convenient if they're in locations that are dangerous or inaccessible.
I think the difference with this system is the fact that we can perform the healing, or the healing happens in situ. So whereas other systems you may have to take the component and put them in an oven, especially if they're thermally actuated. For this system, it happens in place or in situ. The other thing that's really advantageous here is, again, the consistency. So the healing is predictable. We can have a good understanding of what level structural integrity the system is at and how much we can repair to. And the other component is the longevity. And so we've been able to do this an order of magnitude greater than existing self-healing technology out there right now.
I'd say the other thing that gets me really excited is that when you look at our healing potential, we can really get this healing cycle going and complete in about 15 minutes, allowing some time to cool thereafter. And if you look at other work out there, very, very nice work, it's still taking them 2 days to heal these.
One thing that we're looking to do is actually translate this technology and bring it into the industrial setting. We think we've really gotten somewhere where industry and current systems could apply and utilize it. So we're really excited about getting that out into the real world. Certainly searching for partners who can help us develop that, people who are interested in giving us demands or requirements that we could try to meet with this system and make it work. And always, of course, looking for funding partners and people who want to help us deploy this technology. I'm really excited to see some of the groundwork that was laid by predecessors and advisors and people that I had worked with get to kind of their vision and what they were seeing, self-healing materials translating into industry. I also get really excited working with the students. I think they're really passionate about what they do, and seeing them in the lab and really going for it and trying to make a big impact, I think is the reason why I'm here and gets me up in the morning. We're always pushing the front in this lab and trying to do new things and novel things, which is difficult and sometimes is not on the 1 year but more the 5-year time frame, which what this work was. But you keep pushing and eventually you kind of get there. So
I think people just need to keep an eye on what this lab's doing in the next few years, because it's going to be a lot more exciting than what I'm showing you today.